Good morning, sir.
Good morning, all of you. Yeah, I will go to the full screen. Yeah, I hope you can see this screen slide. So this is where we had stopped the last class. So that was basically, we were arriving at a possible definition, reasonable definition for what should be the definition for a one-dimensional Brownian. And also standardize that by taking the expectation to be always zero and the variance as an increasing function, and the simplest increasing function is t itself. So that is why this, what we are going to define, is going to be called standard one-dimensional Brownian. Okay, so here goes the definition. So Bt is a continuous time stochastic process taking value in R. Suppose the following conditions hold. So the starting point is 0, V0 is 0, and t going to Bt omega is a continuous function in t for every omega in capital. So this is what we mean by saying that the sample paths are continuous functions on the half line 0 to infinity. That is the time space. It is taking value in R. B can be negative or positive. Negative means it is going to the left of 0. Yeah. And if you take disjoint time intervals, let's say T1, T2, T3, etc., etc., then you take the net displacement in each of these subintervals, Bt minus B0, Bt2 minus Bt1, Btn minus Bt minus 1, they are all independent random variables. So the process has independent increment property. Sorry, if you want, please note it down. Okay. Yeah. So for any S and T positive, the random variable Bt plus S minus Bs. So this is the net displacement in the interval S to T plus S. So that has the normal distribution with mean 0 and variance T. So the time difference between these two time points is T. T plus S minus S is T. So that sort of says that in this part of the definition, the time homogeneity or stationary independent increment property is implicit. So in any interval of length t, the increment, the net displacement, that is increment in that interval, has a normal distribution with mean 0 and variance. So the increments are normally distributed and time homogeneity holds. This part of the definition only we had sort of heuristically arrived at in the last class. Otherwise, of course, straight away we could have defined this as the Brownian motion and proceeded with it, as we do in many things in mathematics. But since we are going to call it the Brownian motion, it is always better what could be the connection between an object you might have come across in your physics or chemistry as Brownian motion and this. I presume you would have seen Brownian motion in your physics course? Yes or
No.
No. Okay.
No.
Of course, there is no chemistry here. So physical chemistry also it comes across. You can come across. You can look up any write-up on Brownian motion in some Wikipedia and things like that. It might give you a lot of information. And especially one of the earliest papers on Brownian mathematical papers, 1905 by Einstein, that is considered as one of the 3 very major papers of Einstein in the same year. Each one capable of winning a Nobel Prize. course, the most profound of that is perhaps the paper on relativity, for which he did not get the Nobel Prize, because there are no experimental verification for his this thing of relativity theory. That has to wait for several years till they could do some experiments by launching a rocket which will go around the sun and things like that. You didn't have any kind of any this thing in statistical physics in your physics course, right? Heat, thermal physics, statistical physics.
In CMI, the only first semester compulsory course is classical mechanics.
Pardon?
In CMI, the only compulsory physics course for the Math CS students is classical mechanics 1, in which we don't do statistical physics. It's just the until rigid body motion and things
Okay.
like
That also more of an algebraic thing, or there are differential equations are involved?
that. There are different equations to some extent.
Differential equations. Okay. Anyway. So anyway, you can just, as this thing for general knowledge, you can look up Wikipedia, or there may be several sources. Of course, during my student days, there was no Wikipedia. There was only Encyclopedia Britannica. But unlike Wikipedia, Encyclopedia Britannica is supposed to be very authoritative. The sense that the Wikipedia, in principle, its information is not as categorical as the World Encyclopedia Britannica or Encyclopedia Americana and things like that. But that Wikipedia's advantage that if there are errors, somebody subsequently can correct with proper evidence and things like that. So, I mean, it's what you gain in one direction, you may lose in another direction. There are plus points in either of that. So anyway, since the things about Brownian motion, whatever was there in the Encyclopedia Britannica, I presume would be in Wikipedia or some such source available on the net free of charge. Yeah. Okay. So for us, this now we, as a typical math student, we will take this as a definition and we will be happy with it and proceed. So in such a case, this process B is called a standard one-dimensional Brownian. Standard because we are letting the expectation to be 0 for all t and variance to be this particular function, 1 times t. You could have just put some positive constant times t also, that would be increasing and a linear function. If it is a more complicated but strictly increasing function, you can sort of by a change in the time scale, you can come to this. Okay.
Could you go back to the second point? The independent. Could you go back to the independent increments?
It's just like the independent increment property you have seen in the case of Poisson process.
Okay. Got it.
In some sense, any process having independent increment property, the Brownian motion on the one hand and the Poisson process are sort of superimposition of Poisson processes are the kind of building blocks. And a general such process is also called a Levy process. So we will not go into such things. Those will involve a lot of other machinery and things like that. And not only we will call this process a standard Brownian motion, if you anywhere come across a continuous time process, let's say B tilde, taking values in the real line and satisfying the three properties above, such a process is called a standard one-dimensional Brownian. So such a process and this guy B will be similar in law. They will have the same kind of law, that is same kind of distribution. Just like one normal distribution, standard normal distribution, the another standard normal distribution, they have the same probability law in the sense that the distribution each of these induce on the real line is the same, namely given by the standard Gaussian density. Similarly, these processes will also induce some kind of a probability measure on some space, and that space will be the space of continuous functions on 0 infinity. We will not go into such things. So, and that measure is called Wiener measure in honor of Norbert Wiener, whose name was alluded to in the last class. Okay, please note it down. So we now make one elementary remark. Suppose B is a standard one-dimensional Brownian. Let 0 less than S less than T be time points. So from our third hypothesis concerning Brownian motion, note that Bs, so which is basically Bs minus B0 has n normal distribution with mean 0 and variance S. And Bt minus Bs, the time difference between these two time points is T minus S. So that has the normal distribution with mean 0 and variance T minus S. And similar to the first statement here, Bt has normal distribution with mean 0 and variance T. Now note that by the second property, that is the independent increment property, this Bs as well as, Bs and Bt minus Bs, they are independent random variables. And the third one here is the sum of these two independent Gaussian random variables. So please note it down. So since we know about the properties of sum of two independent normal random variables, you can easily verify that Bt, which is Bs plus this thing, has a normal distribution with mean expectation of Bt equal to the sum of these two expectations, so that is 0. And similarly, since these are independent, the variance of the sum is the sum of the variances of the individual ones, so you get T. So there is no inconsistency in the definition. So the definition is consistent. Sometimes when there is a definition, it is also perhaps be good to see if there is any internal inconsistency in the definition. One of the conditions contradicts the other. Sorry, please note it down if you want to. So we will assume that a standard Brownian motion process exists. We are not going to bother about mathematically trying to prove that such a thing, such an object exists. Mathematically trying to prove means we have to get hold of a basic probability space, and on that space, basic set as a sample space omega, on which an appropriate sigma algebra and an appropriate probability measure, on which we will define these random variables bt, and then show that has all these properties. That is going to be a tall order. It will take, that itself might take about half a semester course or more. Basically, one has to develop some kind of a measure theory on function spaces, especially C01 and C0 infinity. And also have to deal with what is meant by convergence of probability measures on such spaces. How does it, what is the relation with the basic topology of that function space, which is a metric space, and so on. Okay. Yeah, so we will assume that Brownian motion exists. Just like in your first probability course, you assume that all those random variables existed. And even now you might be doing that if you have not taken a course in measure theory. Now we will look at the n-dimensional random variable bt1, bt2, btn, where these ti's are in strictly ascending order. So first, this thing is, let us see what is the probability density function of this n-dimensional random. What can we say about that? So take t0 equal to 0. So bt0 is b0, which is equal to 0. So this is just we are taking so that we can write this x, all these xi's in a kind of at one go. Otherwise, we have to, x1 is like that, we have to say, and x2 to xd, xn are in a slightly different fashion. And so this is to sort of unify our notation. So for I equal to 1, 2, 3, n, you take xi is bti minus bti minus 1. So xi is the increment of the Brownian motion in the ith interval here. So since B is the standard Brownian motion, we know that these xi's, that is these guys, are independent random variables, and having respectively, the first one has n0 t1 distribution, then n0 t2 minus t1 distribution, and the last one has n0 tn minus tn minus 1 distribution. So these are all independent normal random variables. Therefore, we know the probability density function of x1, x2, xn, that n-dimensional random. Since vector valued random variables are going to be treated as column vectors, that is why here we have written it here like row vector and put the transpose. So this basically stands for x1, these things stack one above the other kind of. That is x1 first row, x2 second row, and xn the other. Please note it down. So now let us put yi equal to bti. So which is basically BT1 minus BT0 plus BT2 minus BT1, etc., etc., plus BTI minus BTI minus 1. So basically, yi is essentially summation L going from 1 to I of these XLs for each I here. So that is what we have written here separately. Yi equal to x1 plus x2 plus xi for any I between 1 and n. Now here we have these xi's. And here, that is, yeah, these are the xi's. And here the yi's are basically partial sums of these xi's. That reminds us of something which we had done earlier in the course concerning the waiting times of Poisson process. But there, if you remember, we could find the distribution of the n-dimensional random variable W1, W2, Wn, and from there we came to each of these A1, A2, An. Remember, AA was Wi minus Wi minus 1. So in our analysis there, we went back from knowing about yi to xi. Here we are coming the other way around. So the matrix, yeah, okay. Anyway, before that, let me write the vectors. X underline x is the column vector x1, x2, xn, and underline y is this column. Yeah. So if you refer back to our Poisson process 2, page 9 on that, you would see some two matrices, two n cross n matrices, C and C inverse. Here, there we were going from the yi to xi, so we took C accordingly and then C inverse. But here we are going the other way around. So A becomes C inverse and A inverse is C. Remember, this A or C inverse is a n cross n lower triangular matrix with the lower triangular part of it, all entries being 1. That was our C inverse, or rather A, in this discussion. So if you have the old notes with you, your laptop or whatever it is, you can open that appropriate page and see. And you can verify easily. Sorry, if you want, please put it down. Yeah, you can easily verify that y bar or y underline is same thing as A applied to x bar. And other way around, x bar can be expressed as A inverse of y bar. And also it's clear that the determinant of A is 1. So now again, you refer to your theorem which we had stated in our earlier part of this course. The theorem 2 on page 9 and 10 of Poisson process 1. So by that, one can express the probability density function f sub y bar of y in terms of the probability density function of x bar. And of course, there will be 1 over determinant A would also be occurring here, but since that is equal to 1, that 1 over mod determinant A, that doesn't feature here, rather because it is equal to 1. So for any y1, y2, yn, that is y under y bar, little y bar belonging to Rn, the fy bar at little y bar is fx bar evaluated at A inverse y bar, where f sub x is the probability density function of x bar. So here, fx bar, we know it. That's what we had remarked earlier. Yeah. We know the PDF of this, that is fx, f under sub x bar. We know. Actually, there is a this parenthesis is missing. Please put that on. This is the transpose of this whole product. Excuse me. All right. Now take a lowercase y bar, so that y1, y2, yn transpose, that's a vector in Rn, point in Rn. So for such a point, arbitrary point in Rn, note that A inverse applied to y bar is the first coordinate will be y1, the second coordinate will be y2 minus y1, and the third one y3 minus y2, and the last one is yn minus yn minus 1. So for any vector in y, we can find A inverse of 1. That's precisely this. So consequently, we now get from what we have seen earlier, f sub y, y1, y2, yn, which is of course f sub y of y bar, which by this here what we have mentioned is f sub x of A inverse y, and f sub x is at this point is this. It is the, so that is what we are saying, since A inverse y is this point in Rn, so f sub x at A inverse y is f sub x at y1, comma y2 minus y1, y3 minus y2, etc., etc. Please remove this parenthesis. And yn minus yn minus. No parenthesis here. This is typo. And this, all the x1, x2, xn are independent. This PDF of x bar is the product of the individual PDFs. So this guy is precisely f sub x1 at y1, f sub x2 at y2 minus y1, f sub x3 at y3 minus y2, etc., etc., f sub xn at yn minus 1. Because these xi's are independent random variables. So the required PDF of y1, y2, yn, that is bt1, bt2, btn, at any point, we have now expressed as the product of n terms. Each of these is one dimension. Each of this we know. We know that, for example, f sub x1 is the probability density function of n0 t1. And the last one, fxn, this thing, we know that it is a probability density function of n0 tn minus tn minus 2. Please note it down. So we have proved the following result. Let Bt be a standard one-dimensional Brownian motion. Let n be an integer greater than or equal to 2. And t1, t2, tn be non-zero time points in ascending order, in strictly ascending order. Then y under bar, which is the notation for, let's say, that the n-dimensional random variable bt1, bt2, btn. So that has the probability density function f sub y bar at a point y1, y2, yn is equal to f sub x1, sorry, f sub x1 at y1, the first coordinate point, multiplied with f sub x2, y2 minus y1, the difference between y2 and y1. This y2 minus y1 can be negative. Even y1 can be negative and so on. Okay, please keep that in mind. These are not time points. These are any distinct points in R. Multiplied with f sub x3, y3 minus y2, and so on. Finally, f sub xn, yn minus yn minus. Where f sub xi, the ith thing occurring here, is the probability density function of the random variable bti minus bti minus 1. We know that, so that is therefore that is same thing as fxi is the probability density function of the normal distribution with mean 0 and variance ti minus ti minus 1. So you please note it down. So you want me to go back to any of the slides in this derivation? Please tell me. Any questions?
Oh,
Okay. So, but I expected a question. We could have said more. So please note it down. in case you have been distracted by my comment. Yeah. See, suppose X is an n-dimensional random variable having the, n-dimensional normal distribution. You know, n-dimensional normal distribution, see, just like one-dimensional normal distribution is characterized by the mean, that is expectation, and the variance. So the n-dimensional random variable is also characterized by the first two moments. But since it is a vector random variable, of course, the mean would be forming a vector. Mu bar here is mu1, mu2, mu-n, where mu-I is the expectation of the ith component here, xi. And when you since you have more than one random variable, not only variance, but covariances will also come into picture. So you can form the matrix formed by the covariances. Covariances, and the covariance includes variance. So that is called the covariance matrix. The covariance matrix will be a non-negative definite in general, since this is non-singular. This is concentrated on the full n-dimensional space. That will be a positive definite matrix. Some of these things you would have seen in your probability statistics courses. So the n-dimensional normal distribution, let us say, which has two sort of parameters, the mu vector and the covariance matrix sigma. So here mu is a vector in Rn, and sigma will be in general will be a n cross n positive definite matrix. And if A is the non-singular linear transformation on Rn, then you would have seen in your probability or statistics courses the non-singular matrix A applied to X bar. So that is again a vector. That is an n-dimensional random variable that again has an n-dimensional normal distribution. And for that n-dimensional normal distribution, the mean vector would be the A applied to this mu. And the covariance matrix for that is A multiplied with this sigma multiplied with the transpose of A. If this is positive definite and A is non-singular, one can show that this guy is again positive definite. I presume you might be knowing this result already, right?
We did it in measured theoretic probability, BV Rao's course.
Oh, okay, very good. So then there is you have heard it from the even very authoritative source. Good. So that is why I remarked any questions. So I had expected you to answer. We could have said that the nature of the distribution of Y also. Yeah. So this is what we could have said more. The only thing is A mu is very simple here. Since mu is 0, A mu is also 0. What is this guy? The covariance matrix of Y. And I suppose in Professor Rao's course, you would have also been told, and also you must be knowing that how to express the probability density function of this kind of a distribution, that density function in terms of the vector mu and the matrix sigma, right?
Yes.
Good. In statistics course also, you would be doing something about multidimensional normal distribution, right?
There's no statistics course here.
Anyway.
No compulsory statistics course.
Huh?
There's no compulsory stats course here.
Oh, that's an optional course, is it?
Yes.
Okay. Bivariate normal?
I think it was briefly touched upon in our probability course, but I don't entirely remember. The
Yeah,
second
because-
semester probably.
Right. Bivariate normal, one may not sometimes give the way it can be expressed in terms of the mean vector and the covariance matrix. One might be in terms of the 5 coefficients, the means, and also the variance, 2 variances and 1 cross variance, that is covariance. Because see what you have, you will have in the that expression in terms of this covariance matrix sigma and vector mu. If you expand it out, that kind of an expansion is easy to do in a 2-dimensional case, right? Very simple algebra. So that expression we would normally see, and plus the resulting simplification. Okay. So anyway, coming back to our thing, this Y here will have a n-dimensional normal distribution with mean vector A mu and covariance matrix A sigma A transpose. So with this information, now let us see what we can say about our probability, this thing, that distribution of Y bar. Please note it down. Yeah. So in our case, you can easily see that the mu bar is the 0 vector. So now coming to the covariance matrix. Yeah. So that is the distribution of this guy, x1, x2, xn. That has the product of these distributions, densities. So since these xi's are independent, the covariance is going to be 0. Any expectation xi, xj is 0, I not equal to j. So the covariance matrix will precisely be just the diagonal matrix, and the diagonal consists of the variances of xi's. Variance of x1 is t1, variance of x2 is t2 minus t1, variance of xn is tn minus tn minus 1. So the covariance matrix sigma in this case, capital sigma in this case, is the n cross n diagonal matrix where the ith diagonal entry is ti minus 1. Yeah, that's what we are saying. The mean vector mu underscore is 0. And the covariance matrix sigma is the n cross n diagonal matrix. That means off diagonal entries are 0, such that ith diagonal entry is ti minus 1. And as we have mentioned earlier, the matrix A in this case is the n cross n lower triangular matrix with entries equal to 1. That is a lower triangular entries. That is all the entries, the lower triangular part of that matrix is equal to 1. So I leave it as an exercise for you to check that this is the matrix we have to find, which means we have to find its any ijth entry. So it's an exercise for you. The ijth entry of this n cross n matrix A sigma A transpose is precisely the minimum of Ti and Tj. So for example, if n equal to 2, in the 2 by 2 case, this will be the first row will be T1, T1, second row will be T1, T2. T2 is bigger than T1. If it is a 3 by 3, the first row will be T1, 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 second row will be T1, first entry, second entry is T2, and third entry is also T2. The third row, it will be T1, T2, T3. So now you can easily work it out for n cross n. So in an abbreviated notation, one says if B is a standard Brownian motion and T1, T2, Tn are increasing time points, strictly increasing, the random variable Bt1, the n-dimensional random variable Bt1, Bt2, Btn has the n-dimensional normal distribution with mean vector 0 and the covariance matrix given by this Ti minimum Tj being the ijth entry. So I will stop here for the day. So any questions? Okay. Yeah. By the way, your final exam will be an attend in person type exam, that is offline. So all of you will be required to be present in CMI campus during the exam week. I think the exam week is May 9th to 13th. So all the norms concerning such an exam will be in place. And I am targeting 10th of May as the possible date. So I will send an email to that effect today. So if you have no questions or no comments, I think we can end the session for the day.
Thank you, sir.
Yeah. Thank you very much. Take care, both of you, or rather I should say all of you, to pretend that more people are there. Okay. Goodbye. See you.
Take care, sir. Take care. Bye.